Hello everybody, welcome back to the Gregorius Maths video. Let me first address the title of this video. I didn't quite use a random word generator to generate the title of this video. There is some basis for it, and that is that apparently there's a legend in which, in the Battle of Falklands 1914, England versus Germany, the English brought down their missiles, which were designed for the northern hemisphere, to Argentina, which is in the southern hemisphere, for my Americans watching this. And they forgot to adjust the missiles to work in the for the fact that they were in the southern hemisphere, and thus they were much less accurate because of the Coriolis forces in the southern hemisphere versus the northern hemisphere. And I mean, this is apparently just a legend, which is apparently it's just not actually true. But and also, even if it was true, other factors like wind would have more of an effect than the actual Coriolis effect. But nonetheless, it was enough for me to use it as clickbait. So here you are, and I want to just talk a little bit about why it should even matter, mathematically speaking, why it should matter whether you're in the southern hemisphere or the northern hemisphere in the first place anyway. So, the Coriolis effect is given mathematically by the Coriolis acceleration, which is just defined as -2 times by the angular velocity of your reference frame cross the velocity of your particles. So the Coriolis effect is given in a rotating reference frame. For example, the Earth is rotating. And it accounts for the fact that if I just try and just like go in a straight line in a rotating reference frame, because my reference frame is rotating, I'm going to be deflected. At least from the point of view of like an inertial frame. So this is one of the fictitious forces that accounts for the various effects that happen because you're in a rotating frame. And in another video, I will talk about I will derive where the fictitious forces actually come from. This is just one of them. And this is one that deflects stuff to the left or to the right. So anyway, enough yapping. Let's talk about the Earth. If you're on the Earth, we have an axis of rotation, omega, and this is going south to north, or north to south, no, south to north, and we're rotating along this axis, and we have an equator going along like this. I'm going to just draw this in 2D, because if I draw it in 3D, then it would be a disaster. And say we're on the surface of the Earth at a latitude of theta. Okay, we're at a latitude of theta. Now, at this point, if we want to talk about the axis of rotation, we should come up with a local basis in which to work at this angle of theta. So, we'll choose north to be tangent along the surface of the Earth, pointing towards the North Pole. We'll choose up to just be normal to the surface of the Earth. And then I won't draw this on, but pointing outwards, out of the board, we'll have east, which we'll define to be north crossed up. So we have a right-handed set, basically. And yeah, east will point out of the page. And so if we now want to express our angular velocity, if we want to express our angular velocity vector in terms of this basis, we can do this now, because omega hat, say, simply lies in this plane, so we can decompose it in terms of north and up. And if you notice that this angle is theta, so this is pi over 2 minus theta, so this is theta, then you see that omega hat is just given by, if you do the trig, you just get cos theta north plus sine theta up, right? Because if this is pi over 2 minus theta, then cos of that is just sine. Like so. All right, now let's plug this back in here. So at a latitude of theta, our Coriolis effect is going to be given by minus 2 omega times by, where omega is just the magnitude of the angular velocity on Earth, which is quite small actually, times by cos theta. I'm sorry, I don't need to write n hat, do I? No, I have to find it as my basis. My fault. Yeah. Cos theta n plus sine theta. So cos theta in the north plus sine theta up, crossed with our velocity v. So now, for the question of this video, which is why does it matter if we're in the northern or southern hemisphere, we just need to look at this right here, because our latitude can range between 90 and minus 90, so the cos sign will not change. But in the northern hemisphere, our sine theta will be positive, and in the southern hemisphere, our sine theta will be negative. So that's probably where the issues are arising. So, and this accounts for the horizontal deflection, because if you cross it with the upwards, then you just get 0. So this bit accounts for the horizontal deflection, i.e. it affects when you're going in the northeast plane. So let's now look at this. So a horizontal, let's call it, just given by minus 2 omega sine theta up, crossed with our velocity v. So let's break this down into our basis components and look at each one separately. If our motion is north, let's just say v is just given by north, then we get that the Coriolis effect horizontally will just be given by minus 2 omega sine theta and then up cross north, like so. And this will be given by, well, if north cross up is east, then up cross north is minus east, but you cancel out the minus sign, so you just get 2 omega sine theta east, like so. So what does this mean? This means if I was traveling north, suddenly I'm deflected to traveling in the eastern direction. And crucially, if my sine theta is positive, if I'm going north, I'm deflected in the positive direction, east, so I'm deflected to the right. And if I'm going north and sine theta is negative, i.e. in the southern hemisphere, I'm deflected to the left, i.e. west, yeah. And similarly, if we just break it down as, say we're going in the eastern direction now, this means that now our horizontal Coriolis effect, again ignoring the effects on the positive and the upward direction, because that's not the point of today's video. If we're now traveling eastward, what does this do? Well, now the Coriolis effect affects us by doing u cross east, up cross east. Now, up cross east is simply, should simply just be north, I believe. If you move but if you cyclically, no, hold on. It should just be north, I think. I always get mixed up with my cross products, you see. I know that we can cyclically move everything. So hold on, if I swap this signs here, if I have minus e equals n, if equals u cross n, what does that mean? That means n is equal to minus e cross u, which implies that u cross e equals n. Yeah, which is why I wanted to show. Okay, yeah, so it is north. It is just north. Okay, my fault if that was obvious. I just had to work it out for a second. So this is just given by minus 2 omega sine theta n. And again, if I'm in the northern hemisphere, my sine theta is positive, so this whole thing is going south. And if I'm traveling eastwards and suddenly you tell me to go south, I'm turning right. I'm going right. Yeah, if I'm traveling east this way, that's south, right? That makes sense, I think. Yeah, I'm turning right. And similarly, if my sine theta is negative, then you're telling me, okay, you're going east, go north. That's a left turn. So, in conclusion, the Coriolis effect in the northern hemisphere, because of the sign of the sine theta, in the northern hemisphere, it tells me it deflects things to the right, horizontally, and in the southern hemisphere, it deflects things to the left. And so when we valiantly fought the Germans in Argentina, our missiles were off because we were accounting for them being deflected to the right, but we forgot that we were in the southern hemisphere, so we should have been accounting for them being deflected in the left. And yeah, there you go. That's that, and I'll hopefully see you tomorrow. Good day.